Hello and welcome to Math Zone African Motives. In this tutorial, we will be tackling a comprehensive thermodynamics problem step by step. Our goal is to walk through each part of the problem from start to finish, ensuring you understand every formula, calculation, and concept. We'll be working with a polytropic compression process, calculating various thermodynamic properties like volume, temperature, work, internal energy, and heat flow. By the end of this video, you will be able to apply the ideal gas law and the first law of thermodynamics to solve complex problems. Let's get started. First, let's carefully read the entire question. Remember, the question often contains subtle but critical pieces of information. Question 1. 0.454 kg gas is compressed according to the law. PV to the power of n equals C, where n equals 1025 from 138 kilopascals and a temperature of 15 degrees Celsius to a pressure of 2070 kilopascals. R equals 0.3 kilojoules per kilogram. Kelvin and C sub V equals 0.712 kilojoules per kilogram Kelvin. It continues with a set of calculations we need to perform. Calculate the following. 1.1 the original and final volumes. 8. 1.2 the final absolute temperature. 3. 1.3 the work done in kilojoules. 3. 1.4 the change in internal energy. 3. 1.5 the heat flow through the cylinder walls. 3. 20. This problem is about a polytropic process, specifically a compression, because the pressure increases from 138 kPa to 2070 kPa. A crucial first step in any physics problem is to list the given data and identify the unknowns. This helps us organize our thoughts and choose the correct formulas. Here is a summary of the data provided in the question. Notice that the initial temperature is in degrees Celsius. In thermodynamics, we must always work with absolute temperature. So, our first conversion is to transform Celsius into Kelvin. The formula for this is simply T in Kelvin equals T in Celsius plus 273. For this problem, T1 equals 15 plus 273, which gives us an initial absolute temperature of 288 Kelvin. Now let's list our unknowns, the quantities we need to find. We need to find the initial and final volumes, V1 and V2, the final temperature, T2, the work done, W sub GD, the change in internal energy, delta U, and the heat transfer, Q. Let's begin with part 1.1, which asks us to find the original or initial volume. The question is, calculate the original volume. To find the initial volume, V1, we can use the ideal gas law as we have the initial pressure, mass, gas constant, and temperature. The ideal gas law is P times 5 equals M times R times T. We need to solve this for V1. Rearranging the formula gives us V1 equals M times R times T1, all divided by P1. Now let's substitute our known values into the equation. V1 equals 454 times 0.3 times 288, divided by 138. Calculating this gives us an initial volume of approximately 0.284 cubic meters. We'll round this to 3 decimal places. So we've successfully calculated the original volume of the gas. Next, we need to find the final volume, V2. Since this is a polytropic process, the relationship between pressure and volume is governed by the polytropic law. The law for a polytropic process is P 1 times V1 to the power of n equals P 2 times V 2 to the power of n. Our goal is to solve for V2. To isolate V2, we first divide both sides by P2. This gives us V2 to the n equals V1 to the n times the ratio of P1 to P2. To get V2 by itself, we take the nth root of both sides, which is the same as raising both sides to the power of 1 over n. The resulting formula for V2 is V1 times P1 divided by P2, all raised to the power of 1 over n. Now we can substitute the values we know into this equation. V2 equals our calculated V1 of 0.284 times the ratio of pressures 138 over 2070, raised to the power of 1 over 1025. Notice how we use the more precise value for V1 to ensure accuracy. Calculating this gives us the final volume, V2, of approximately 0.0325 cubic meters. So the volume has decreased significantly during compression. We have now successfully found both the original and final volumes. Let's move on to part 1.2, which requires us to calculate the final absolute temperature, T2. The question is, find the final absolute temperature. Similar to volume, the temperature and pressure in a polytropic process have a specific relationship. The relationship is T2 over T1 equals V, 1 over V2, all raised to the power of n minus 1. We need to solve this for T2. Multiplying by T1, we get the formula for the final temperature. T2 equals T1 times the ratio of the volumes raised to the power of n minus 1. Now we substitute our known values into the equation. We'll use the precise values for V1 and V2 for better accuracy. T2 equals 288. Our initial temperature times the ratio of volumes, 0.284 divided by 0.0325, all raised to the power of 1025 minus 1, which is 0.25. Performing this calculation, we find that the final absolute temperature, T2, is approximately 495,167 Kelvin. As expected, the temperature increased due to the work done on the gas during compression. This value matches the one in the provided solution memo. We've now calculated the volumes and final temperature. It's time to move to the energy calculations. Let's start with part 1.3, the work done. We need to calculate the work done in kilojoules. There are two primary formulas for the work done in a polytropic process. The question memo shows both, so we'll work through both to demonstrate. Method 1 uses the pressures and volumes at the initial and final states. The formula is W sub D equals P1V1 minus P2V2, all divided by n minus 1. This is one of the standard equations for polytropic work. Let's plug in our values. Be very careful to use the correct pressures and volumes for each term. W sub D equals the quantity 138 times 0.284 minus 2070 times 0.0325, all divided by 125 minus 1. Calculating this gives us the work done, W sub D, of approximately negative 112,000 BU kilojoules. The negative sign is important. It indicates that work was done on the gas, which makes sense for a compression process. Now let's verify this result using the second method for calculating work done in a polytropic process. Method 2 uses the mass, gas constant, and the change in temperature. The formula is W sub D equals m times r times the quantity T, 1 minus T2, all divided by n minus 1. We have all these values from our initial data and previous calculations. Let's substitute them in. W sub D equals 0.454 times 0.3 times the quantity 288 minus 495,167, all divided by 1025, minus 1. This gives us a result of approximately negative 112,865 kilojoules. We see a slight discrepancy between the two methods. This is due to the cumulative effect of rounding at each step, especially the values for V1 and V2. The question memo's answer is based on method 1. For the purpose of this tutorial, we will use the value from method 1 to ensure our subsequent calculations match the memo, as it's the most common starting point for these types of problems. That value is negative 112,332 kilojoules. So our final result for work done is negative 112,332 kilojoules. Now for part 1.4, where we calculate the change in internal energy. We need to find the change in internal energy, delta U. A key concept to remember is that the change in internal energy, delta U, for an ideal gas depends only on the change in its temperature, not on the path of the process. The formula for the change in internal energy is delta U equals m, the mass, times C sub V, the specific heat at constant volume, times the change in temperature, T2 minus T1. Let's substitute our values into this formula. Delta U equals 0.454 times 712 times the quantity T2 minus T1. We will use the precise value of T2 we calculated earlier, 495,167 minus 288. Let's calculate the value inside the parentheses first. The change in temperature, T2 minus T1, is 207,167 Kelvin. Now we complete the multiplication. Delta U equals 0.454 times 712 times 207,167, which gives us approximately 60,966 kilojoules. This positive value indicates that the internal energy of the gas increased. This value perfectly matches the result in the memo. We've reached the final part of our calculation, part 1.5, which asks for the heat flow through the cylinder walls. We need to calculate the heat flow Q. To find the heat transfer Q, we will use one of the most fundamental laws of thermodynamics, the first law of thermodynamics. The first law states that the heat added to a system, Q, is equal to the work done by the system, W sub by, plus the change in the system's internal energy, delta U. It's extremely important to pay attention to the work term. The formula uses work by the system. In our case, work was done on the system during compression, so the work we calculated, W sub D, is the negative of W sub by. This means that W sub by equals negative W sub D. Let's substitute this into the first law. The law becomes Q equals negative W sub D plus delta U. Now we substitute the values we calculated. We'll use the work done from method 1, which was negative 112,332 kilojoules. Q equals negative 112,332 plus 66,966. The negative of a negative is a positive, so this simplifies to Q equals 112,332 plus 66,966, which gives us a heat flow Q of 179,298 kilojoules. This means 179,298 kilojoules of heat were added to the system. However, let's look at the memo's answer for this part. It shows Q equals negative 45,366 kilojoules. The memo gives an answer of negative 45,366 kilojoules. This is a significant discrepancy. Let's trace back where the memo's answer comes from to identify the error. If you look at the memo's calculation, it uses the formula Q equals W sub D plus delta U and directly substitutes the negative value of W sub D. The error lies in the application of the first law. The formula Q at W plus du is often written, but the sign convention for W is critical. The most common convention is Q equal W by plus du, where W is work by the system. If the memo were using a convention where W meant work on the system, the formula would be Q equal W on plus du, which is the same as our formula. The memo seems to have used W on in the formula for W by. Therefore, we have identified an error in the memo for part 1.5. Based on the standard application of the first law of thermodynamics and the calculated work done, the correct heat flow is positive 179,298 kilojoules, meaning heat was added to the gas during this polytropic compression. To recap, the memo's answer is incorrect. The first law, applied correctly, gives us a heat flow of 179,298 kilojoules. Let's quickly summarize what we've accomplished in this detailed tutorial. We started with a complex thermodynamics problem, extracting and converting all the necessary data. We then calculated 5 key properties of a polytropic compression process. Here is a summary of all our final correct answers. We learned how to use the ideal gas law to find volume, the polytropic law to find the final volume and temperature, how to calculate the work done using 2 different methods, and how the change in internal energy depends only on temperature. Most importantly, we saw how to apply the first law of thermodynamics and critically evaluated a potential error in a solution, reinforcing the importance of correct sign conventions for work. Thank you for watching this tutorial. I hope you found it clear and helpful. Subscribe for more tutorials from Math Zone African Motives to continue building your understanding of key mathematical and scientific concepts. Subscribe for more tutorials from Math Zone African Motives. See you next time.